What's up, everybody? Hope you all are doing well. Today we are going to be solving the inclined plane problems, also known as an object on a ramp. And we're going to go ahead and derive the acceleration of an object on an inclined plane. So there really are, for all these force problems that we're doing, there's really three steps that you want to take, three basic steps. Step number one is you're going to draw your free body diagram, or FBD. Step number two is you're going to I'm going to call it fixing your FBD. In other words, what I want you to do is to have everything just in X, Y coordinates. So change your free body into X's and Y's only. And then the third step is to go ahead and do your summations. So we'll sum up our forces in the horizontal direction, sum up our forces in the vertical direction. And you can pretty much do this for every single force problem that we're going to look at in this unit. Alright, so let's go ahead and get started. Step one, draw your free body diagram. So we're going to go ahead and do that on the mass here. So we have kind of the obvious one, which is going to be the weight acting on the mass, or the force of gravity. The next thing we're going to look at is the normal force. Now remember, the normal force, or the force coming from the surface, is always going to be perpendicular to the surface. So in some of the problems when we were just on a flat surface, it'd be straight vertical. This one is going to be, again, perpendicular to the surface, so as the angle changes, this normal force would also change. Now in this problem, it also says that there's friction. So remember, hopefully you can see that this object's going to start to move down the ramp this way. So friction will always oppose that direction of motion. So friction's going to go up the ramp this way, and it's going to be parallel to the surface of the ramp. So that's step one, drawing out our free body diagram on the object. Step number two, we're now going to fix this. Okay, now for this one, oftentimes in problems we fix the forces. In this one, we're actually going to change the whole coordinate system. So in other words, if we're used to a coordinate system that looks like this, like, horizontal is X and vertical is Y. What we're going to do is we're going to actually rotate our coordinate system. So we're going to rotate it so that the X direction represents the direction of motion of the object. And then the Y direction would be, well, it'd be perpendicular to that direction. Okay, and so in this case, by rotating our coordinate system, it actually makes the problem easier. It's one of these situations where we make the problem harder to make it easier. So what I want you to notice then, as we go ahead and try to fix our X's and Y's, is that our normal force, our normal force is already in our Y direction, right? And our friction is in our X direction. So those two we can leave alone. That means the only force that we have to fix is this force of gravity, which is going straight down. So let's go ahead and do that. So when you look at this picture here, we're going to go ahead and draw two components that are now in our new coordinate system. So in other words, here's our perpendicular. We have one component we'll call FG in the X direction. So that's going to be, again, in this new X direction here. And you can think of this as the force of gravity causing the object to move down the ramp. This is the amount of gravity pulling the object down the ramp. And then we have this component over here, which we'll call the force of gravity in the Y direction. This is actually the component that holds the mass on the ramp. Okay, keeps it from flying off the ramp. So next, we got to fix it, right? We got to find out how much those are. So we're going to have to do a little bit of geometry here. So check this out. This angle is theta right here. And if you look at the force of gravity, this is perpendicular. So that means this angle must be 90 minus theta, right? But then this is also perpendicular to here. So if this is 90 minus theta, this must be back to theta, right? Or 90 minus theta minus theta. 90 minus 90 minus theta, which means that's going to also be the angle. So hope you caught that. If not, that's okay. Just remember that this angle inside here is always going to be the same as this angle right here. Okay? All right, let me clean this up a bit. Let's actually just put this off here into the corner. So once again, this is our MG here. Let's redraw this triangle. This and this goes like this. Okay, oh, sorry, I skipped a step. MG, remember, FG is going to be equal to MG. And then this is our angle theta. And then we just solve our kind of our right triangle. So this is the adjacent side right here. So we can write this as MG cosine theta. And then on this side, we're going to write MG sine theta. This is our opposite side. So if we go back, let's redraw this free body. And we're just going to put x's and y's here. So the normal force was the same. Friction is also the same. And then our new gravity components. So the one coming down the ramp, this is this guy right here, mg sine theta. That's the component of gravity that's kind of pulling the object down the ramp. And then this piece right here is our mg cosine theta. Once we've done this, we can now easily do our summations, right? Because we now have our x's and y's all set up. So let's do our summation. So we're going to do the sum of the forces in the x direction. So we just take a look at our two forces in the x direction. That's going to be mg sine theta. Remember, this is the component of gravity pulling the object down the ramp. And then we're going to subtract out friction. And this is equal to mass times acceleration. So this is the object that's going to be accelerating down the ramp, right? Now let's do our summation in the y direction. So for this one, we have the normal force going up, and then we're going to subtract mg cosine theta coming down. This one we're also going to do ma. Now remember, these are two different a's. This is the a in the x direction, this is the a in the y direction. However, remember, our object is sliding down the ramp like this. So there is no vertical acceleration. So in other words, we can say this is going to be 0. So notice what happens. Our normal force is essentially going to be equal to mg cosine theta. So just to recall, when we were like on a flat surface, if we were just simply on a flat surface, we'd have gravity mg, we'd have normal force up, and those two would be equal to each other. We'd say Fn is equal to mg. But when we're on an inclined plane, the normal force is going to be less. Okay, hopefully that makes sense, because in case 1, all of gravity is pulling down, so the normal force is going to be the exact same thing, pushing up. But when you're on a plane, when you're on a ramp, some of gravity is pulling it down. And so less of it is going to be pushing back up this way. So I was asking to solve for the acceleration. I just want to point out this is like most of the physics of the problem. The rest is just going to be algebra. But let's go ahead and solve it anyways. So let's go ahead and move this up even more. We'll keep our two summations there. So we're going to go ahead and solve for acceleration. So let's take the first equation. We do want to solve for friction. Remember, friction is equal to mu times normal force. And we just found the normal force. So we can write that as mu mg cosine of theta. Right? We'll just substitute in our normal force right there. So let's go ahead and write out the full equation. We have mg sine theta minus mu, friction, right? Mu mg cosine theta equals mass times acceleration in the x direction. Now notice what happens here. We have mass, mass, mass. So since we have mass in all three terms, we can actually cancel out the masses. So what are we left with? We're left with g sine theta minus mu g cosine theta equals a. So conceptually, let's look at this conceptually. Conceptually, this is the acceleration trying to pull the object down the ramp. In fact, if there was no friction, if friction was 0, then this would be the exact acceleration. So notice it's going to be a little bit less than 9.8, or depending on the angle, which should make sense. And then this is the component of friction that's going to be kind of, slowing down that acceleration or decreasing that acceleration. All right, hope that was helpful. Please let me know if you have any questions, and I'll see you in the next one.